All right. Can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey for another great presentation here on site. So, a couple things. We are live streaming this on our YouTube. So, if you ever can't make it, you can always catch us there as we live stream. Or if you miss us entirely, you can always go back and watch the video. That being said, while a couple people are getting settled out here, you can check us out on our website, uacnj.org. That's where you will find a list of all our events, our upcoming talks, and you can get information about the telescopes on site, as well as what presentations you can see. For the people here, a couple safety things. If you need to use the bathroom, we got the porta potty to my right, your left. We do have a little gift shop and museum area set up through the door to my left and your right. We are slightly overcast, but much better than last week, which was a bit rainy. Where it looks like we do have a couple of observatories open that we'll be able to observe through after the presentation. That being said, when we do go to leave here tonight, we are using our headlights because we don't like getting run over. I'm sure everyone can agree that that's not a great feeling. So again, headlights on when we leave. However, if we're using flashlights or like the light on our cell phone to walk around, we are keeping those pointed towards the ground. Because as much as we like not running people over, we also like not needlessly blinding people by random flashlights in their face. Right. So with that, looks like we got through most of that. So our talk tonight is The Life Cycle of Stars with Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's. Is it Halley's or Halley's?
I say Halley's.
Halley's Comet. Walt's a member of the North Jersey Astronomical Group and the Rockland Astronomy Club. He's been coming up to Jenny Jump for over 20 years, and with that, we're going to get the show on the road.
Thanks. So basically, all she told you about was that I'm old, but I do love looking at the stars, and I'm really excited with all you folks showing up. Thanks a lot. Would have been really strange if nobody did. I'm going to be talking about stars. And, you know, stars aren't only interesting in and of themselves. They create some interesting objects out there that we can see. We'll probably even see some tonight if the clouds behave themselves. So we're going to spend some time looking at a typical life cycle of a star like our sun. But first I'm going to just spend a few minutes talking about some star science basics. So astronomers define the brightness of a star two different ways. They talk about apparent or visible magnitude and absolute magnitude. And a good way to think about that is on the left you see there's one car is closer than the other car. If their headlights are the exact same brightness, obviously the car that's closer to you is going to look brighter. And it's the same with stars. So that's apparent magnitude, how it appears in the sky. Now absolute magnitude, if you have a truck with very bright lights on and the same car, truck A, even though they're the same distance, truck A is going to look brighter than the car. And that's called the absolute magnitude. So apparent magnitude is very important to visual astronomers. Why would you think that is? Well, to visual astronomers, especially before these fancy telescopes that have GPS and they can just point at stuff, we used to have to do star hopping. So we'd use a map that would show us the apparent brightness of the stars, and we'd go to the brightest star and we'd hop to the next dimmer star and the dimmer star until we got to the object that we wanted to see. And so the star maps help you find where you are in the sky based on the brightness of the stars, the apparent brightness. Now absolute magnitude is important for doing science. We need to know if two stars are next to each other, which would be brighter and by how much. And this, along with the star spectrum, gives us all kinds of clues to the size and the characteristics of the star we're looking at. So when you're doing science, you really need to know what the absolute magnitude of the stars are. And the absolute magnitude is calculated as if both stars were 32.6 light years away. That's 10 parsecs. So that's the standard. But if you're talking about planets, it's 1 astronomical unit. They're normalized to 1 astronomical unit, which is 93 million miles, the average distance of the Earth from the sun. And here's a list of some of the common stars. You know, the magnitudes go all the way back about 2,000 years to the Greek astronomer Hipparchus. And so he would say the brightest stars are of the first magnitude. And just over the years, it's gotten into a scientific way of measuring things. And it's really not that great because to normalize it, there's some stars that are negative magnitude because they're brighter than the first magnitude stars that the Greeks identified 2,000 years ago. So the limit of the Hubble telescope is about 30, a magnitude of 30. Your eye can see about a magnitude of 6. If you look at the full moon, that's a negative 12.5. And the sun is an eyeball scorching negative 26.8. So the brightest stars are right around 1, 0, -1. Those are the brightest stars in the sky. One more thing we need to understand is electromagnetic spectrum. And that's everything from radio waves all the way to gamma rays. It's a huge spectrum of electromagnetic radiation. And we just see a tiny sliver of that in visible light. And that would be right here. That's how much of the spectrum we can actually see with our eyes. The rest we have to detect with instruments. So it covers everything from the radio waves right up to the gamma rays. Now let me give you an example of how important it is to know or to have ways of looking at stars outside of the visible spectrum. We'll take a quick look at a star factory called the Eagle Nebula. This is a very cool object. It's basically a star factory. The way stars are formed, and we'll get into this a little deeper, is clouds of gas start to collapse on their own gravity. And finally, at some point, they get hot enough because of the gravitational traction to get hot and go light up to a protostar of about 2,000 degrees Kelvin. And then after that, after a while, they get hotter. And so here we see some stars that are blinking into existence. Once they ignite, they're burning under nuclear fusion. And this picture was taken in visible light. So the Hubble telescope photographed this in the same light spectrum that our eyes could see. If we look through a telescope, though, we would just see clouds. We would see what looked like clouds. We wouldn't see these colors. Our eyes act like a camera shutter of like 1/30th of a second. And the Hubble takes hours of light into its sensors, and that's how you get the pure color. Thank you. So let's take a look at what the Hubble recorded under infrared light. Very different picture. It's the exact same field of view, but it's certainly different. The IR sensors cut through a lot of the dust because they are measuring heat. And so they see the stars where we didn't. Here's a side by side. They both give important information. One about the structure of the dust and just that it's there, and the other shows us much more clearly how many stars. And still, these clouds are so thick, the infrared couldn't even cut through all of it. So what do you think that is? It's nothing. It's just a random distribution. When you have when you're doing data sampling and there's no correlation, you expect those dots to be all over the place, and that's what a random distribution looks like. But if the two axes that you're plotting against have some kind of correlation, you would expect there to be patterns. And there's some very interesting patterns. That's an HR diagram taken after Hertzsprung and Russell. And it was a major step in our knowledge of stellar evolution. They discovered when you plot how bright a star is, the luminosity in absolute magnitude, against the temperature. The stars are not randomly distributed, but they form into clusters. So when you look at the location of a star on this graph, you can tell a lot about it. Its luminosity, its spectral type, its color, its temperature, its mass, its chemical composition, its age, and the evolutionary history. That's the kind of diagram that I looked at for years and years. And then they came out with some really nice color ones. Here's a nice one. And you can see that right here is the sun. This is called the main sequence. And stars spend most of their life on the main sequence. It's kind of like the periodic table of elements, except the periodic table of elements, the elements never change. Where here, when a star starts running out of hydrogen to burn, it moves away on this table in evolution through the HR diagram. And in about 5 billion years, our sun will leave the main sequence and start moving towards the red giants. This just gives you an idea of how long stars live depending on how hot and how large they are. For a star that's 60 times as large as our sun, you expect it only to live about 3 million years. It's very hot, very large. Our sun, which is one solar mass, everything's measured in solar masses here, so our sun, one solar mass, has a lifespan of about 10 billion years. So we're good for another 5 billion years, you should be glad to hear. And then we've got the brown dwarfs and the dwarf stars. They live for trillions of years, we think. Right? Since the universe is only about 13.8 billion years, we really don't know what the lifespan of these stars are. But they've already stopped having nuclear fusion and they're just cooling off. This is another HR diagram with lifespans. I'm just going to go past that. Now remember that photo of the Eagle Nebula I showed you? This is a wider view of it. And there's those 3 pillars. So these pillars are like 4 light years long. It takes 4 light years for light to travel from here to there. And it's in the huge nebula with a star cluster up here. These are young, bright, hot stars, the stars that don't last very long. They burn themselves out very quickly because they're so massive and they're so hot. And the interesting thing that I found is that earlier infrared images in the mid-infrared led scientists to believe that those stars went one of those stars went supernova 6,000 years ago. And if it did, it would have blown away these pillars. So why do we have a picture of this? Well, because the pillars are actually 6,500 light years away. So we're looking at light from about 4,000 BC. It's 6,500 years old. And so if those pillars really were blown away by a supernova, it'll take us another 500 years to see if the scientists were right or not. So that's a low-risk call on the scientist's part. Not too many people will be around. Certainly the people writing their paychecks won't be around. But the Eagle Nebula is just an amazing nebula out there. And this is my favorite HR diagram. And what I like about it, these are the hottest stars, and these are the coolest stars. So those are the spectral class. Our sun is a G. Our sun sits right here, very boring kind of a place, very middle of the road. But again, you can see as you go this way, the stars get cooler. And if you go this way, the magnitude increases. So what this is showing you is that for any given temperature, and it's common sense, for any given temperature, the brightest stars are going to be the biggest stars, right? If they're 2 stars, same temperature, the bigger ones are going to be the brightest. And so here we have the big ones on top. Even the dim ones, when you get to be this big, you can still shine a lot of light, like Betelgeuse. We'll see that. in a minute. Uh, the surface temperature of our sun's about 10,000 degrees Fahrenheit. It kind of felt like we were standing on the sun today, but it's still a bit more, a little bit hotter. They actually measure star temperature in Kelvin, so it's 5,800 Kelvin, but 10,000 Fahrenheit. So we're just going to take a look at some size comparisons, so you get an idea of what the variation of the sizes of the stars are. Put it in perspective. And this is a picture of Jupiter. It's not a star. It's our largest planet. But what it shows you is back in 1994, July, there was a comet Schumacher-Levy, broke up into 21 pieces, and they hit the back of Jupiter. And then as Jupiter rotated into our view, we started to see the scars from that comet. It was a really cool time to be into astronomy. And so each of these is about the size of the Earth. And that's why I put it there, just to give you an idea. So our moon is about 2,000 miles in diameter. The Earth is just under 8,000 miles in diameter. Jupiter is 86,000 miles in diameter. And the sun is 10 times that, at 864,000 miles in diameter. And the sun can hold about 1,000 Jupiters. It's 10 times the diameter, but it'll hold about 1,000 Jupiters. So that kind of gives you an idea. Earth is about the size of what we would call a white dwarf, and we'll be talking about them later. So the white dwarfs are going to be the smallest, and they're going to be about this size. And then you got Jupiter, and 1,000 of these Jupiters can fit inside the sun, which is just a regular sized, boring kind of a star. So here's the sun, and here's how it stacks up to some of the others. The diameter of Arcturus is about 21.96 million miles, and it's the brightest star in Bootes. Whatever the brightest star in a constellation is, they call that the alpha. So this is also called Alpha Bootes, but some stars actually have names, and Arcturus is the brightest, is this one. We can see this tonight. If you look and you see the Big Dipper, look for the curve of the handle and follow the arc to Arcturus. It's easy to remember, and it'll be the brightest star as you follow the arc, and it'll be it's the brightest star in Bootes, and Bootes looks a little like a kite. So from Arcturus you'll see kind of like a kite shape, and you can just see that with your bare eyes if the clouds will let you. Okay, Arcturus isn't looking too big now. The red giant Betelgeuse has a diameter of 1 billion miles, and if it were where the sun is, we would be inside it. A matter of fact, it would go all the way out to Jupiter. And spoiler alert: when our sun starts to loses its hydrogen, it's going to expand into a red giant, and we will really get hot then. Betelgeuse is the brightest star in Orion, so it's called Alpha Orionis. That's mainly a winter star, but it really depends on how late you're willing to stay up sometimes in the late summer to see it. It's the 9th brightest star in the sky, and is part of the winter triangle. And then we have a red supergiant, Antares. It's 604 light years from Earth. It's 700 times the diameter of the sun, but its density is only 1/1,000,000th that of the sun. So it's much, much less dense because it's coming from a dying star, and the gravity has lessened so that the star is just getting bigger and bigger, but it's the same amount of material. So it's a lot less dense. And that's also known as the heart of Scorpion. That's another from here. That's the 15th brightest star in the night sky, and its exact size is uncertain. And by now, the sun doesn't even take up a pixel on this screen, right? The size of the sun, and forget about Earth and Jupiter. And now here's Antares next to one of the largest stars that we know of. W Cephei is one of the largest known stars. It's an uncertain size. We estimate it to be somewhere around 1,050 to 1,900 solar radii. So that's a lot bigger than our sun. Its photosphere would reach almost to Saturn. So this thing is huge. It's about 5,000 light years from us. So as I've said, a star's position on the HR diagram shows where it's at in its lifespan. And this is the main sequence of the HR diagram, as I've said before. The sun's sitting right here. So I'm going to talk about what happens to the sun when it starts to run out of hydrogen to burn. Now, as I've noted, the way it's created is dust collapses in its own gravity. And it spends about 100,000 years as a collapsing protostar, about 2,000 to 3,000 degrees Kelvin. It gets hotter under the gravity. And after a few million years, as a very wild and erratic star known as a Tauri star, it reaches hydrostatic equilibrium. And what that means is that the gravity that's trying to pull the star together and the radiation of the nuclear fusion is pulling out, and they finally equalize. So the outward force and the inward force, and that's how the sun spends 10 billion years of its life on the main sequence. The main sequence stars have all reached hydrostatic equilibrium, and they just go along burning hydrogen. When they run out of hydrogen, that's when all the changes start taking place. The sun's been on the main sequence for about 4.6 billion years. It's still got about 4.5 to 5.5 billion years left on it. Plenty of tread on those tires. Every second, 600 million tons of matter are converted into neutrinos, solar radiation, and a whole lot of energy. The precise position of a star on that main sequence really depends on how much hydrogen, the mass of hydrogen in that star that it has to burn. That will determine. Core temperatures can be as high as about 107,000 Kelvin, which is 192,000 degrees Fahrenheit. Helium starts to form in the core as hydrogen atoms are fused. At temperatures above 108 Kelvin, the heavier elements like carbon and oxygen start to form. So stars are where we get our heavier elements from. They are made in those nuclear furnaces. Bigger stars make heavier elements than the lighter stars. So I'm still talking about a star that's about the size of our sun, anywhere from 1 to 5 to 8 times the size of the sun is what I'm talking about here. So the core shrinks as hydrogen is converted to helium, and gravity increases, as does the nuclear fusion. So the sun gets 1% brighter every 100 million years. And so in 1.1 billion years, it gets about 10% brighter, which may trigger a moist greenhouse effect and head us towards another Venus-like situation. In 3.5 billion years, it will be 40% brighter. So at that point, oceans will boil. No matter whether you're driving a carbon car or an electric car, you know, when the sun gets to be that hot, the oceans are going to boil until it starts burning helium. The sun will then grow to a red giant, like Betelgeuse that I showed you. It's going to expand. We will most likely be inside it, and it'll swallow up Mercury, Venus, and then us. At that point, it will have only about 120 million years left on its life. So we're talking about very near the end of its 10 billion year life. And in that time, near the end of its life, there'll be what's called a helium flash, as 40% of the sun mass turns into carbon. And that in itself is pretty interesting. I read a chapter in a book just talking about, you know, for life to form, you really need carbon. Carbon is a complex molecule that can carry genetic information, and it's absolutely essential to life. And so here we have carbon being a major product of stars, small ones and large ones alike. For a small one like the sun, carbon's about the last element that it forms. And over the next 20 million years, the sun will become unstable, and it'll eventually throw off half of its mass into what's known as a planetary nebula. So the gravity's lessening, and it throws off about half its mass into this giant, very pretty cloud. I'll show you some pictures of it. And the rest of it will become a white dwarf. So half the mass of the sun will become a white dwarf. It'll cool for a few trillion years. In 10 to 20,000 years after that ring around the planetary nebula is formed, it will dissipate. So that's only around, for astronomically, a short period of time, 10 to 20,000 years. But they are very beautiful. And I want to show you a couple of pictures of some. Here's a ring nebula. It's about 1630 light years from us in the constellation Lyra, which tonight will be right over our head. There's a chance that someone will put the ring nebula in a telescope, and it'll look like a very small smoke ring. It's very cool. The Hubble even catches the white dwarf, magnitude 15 star, right in the middle of that planetary nebula. And planetary nebulas have nothing to do with planets. It's just that when Messier was looking for comets back in the 1700s, there were objects up there that were not stars, but they were fuzzy, and he didn't want to be distracted by objects that he saw all the time and knew they weren't comets. So he named them nebula, and in this situation, because they're generally round, he called them planetary nebula, planetary shapes, and that's how they got their name. Also, the colors are added by NASA processing JPL labs, and they color those things to denote different elements. So blue color is helium, the cyan color is hydrogen and oxygen, the reddish color is nitrogen and sulfur. So you can tell what elements are in there. Now again, we'll switch our instrumentation and we'll add some infrared information to this picture. Pretty different, isn't it? This is what we were looking at before. This is all the extra information that we could not see in the I'm not going to be able to see my notes is what I'm not going to be able to see. I know. I'm bad. I guess I'll take the time to clip it. Okay. So you look at this, you could almost feel the shock wave shooting out here. And that was not from when it blew off ejected its shell to make the planetary nebula. This actually happened 10,000 to 100,000 years earlier. The residue stellar winds blew out gas before it even got rid of its shell. This is a combination of the Hubble telescope and some ground-based telescopes, a large binocular telescope, and also the Subaru telescope, which records hydrogen alpha, which is always red. You always see hydrogen alpha as red in these pictures. Here's another interesting planetary nebula. This is the Dumbbell Nebula, and it's full of knots of gas. The length of streets vary from 11 to 35 billion miles long, several times larger than from the sun to Pluto. And they form an interface between hot ionized gas and the cool neutral part of the nebula. This was taken in 2001. Again, oxygen's in blue, hydrogen's in green, and sulfur and nitrogen are in red. This is one of my favorite planetary. The Cat's Eye Nebula. This is a mystery to scientists. It was formed by a star that was very close to our sun's mass, so it's almost like a sister star formed this. And Hubble revealed details that we had never seen before, which are these rings. Now they look like rings to us, but what they really are is they're bubbles of gas. and there's like 11 plus bubbles of gas here. And the view that we have is if you took an onion and you just sliced it in half and then looked at the onion rings. That's what you're looking at there. And it's a bullseye pattern of 11 or more concentric rings, and each ring is actually the edge of a spherical bubble. Observations suggest that the star ejected a series of pulses at 1,500-year intervals, and it's really got scientists scratching their heads over this, because there's all kinds of theories, and people really don't know what exactly caused those rings. Some think it might have been cycles of magnetic activity. Some think it's action of a companion star that we didn't see orbiting around the white dwarf. Stellar pulsations, material might have been ejected smoothly from the star, and then the rings were created later due to formation of waves in the outflowing of the material. We just don't know. So that's one of the mysteries. Maybe we'll get some better information from the James Webb Telescope. And I'm going to be talking about that in September. Sometime in September, I'm going to get the James Webb shots, and we're going to look at them versus the Hubble and see just how much better the resolution is, and what is it going to do for us? What are our couple $2 billion going to do for us? This is called Hubble spirograph. Another one that the Hubble really gave us some great detail on. 22 years ago already. This shot's from. It's called IC418. It glows like a multifaceted jewel. It's just amazing. Intricate patterns. It lies about 2,000 years from us in the direction of the constellation Lepus. Again, the picture's been enhanced to designate the different camera filters which they used to show the different elements that are out there. So all these planetary nebulas started out similar to our sun. They're small stars between 1 and 8 times the size of our star. They didn't go supernova. The stars, our sun size, do not explode like a supernova. They get big and they blow out a shell of gas, which causes a planetary nebula, and then they just very undramatically turn into a white dwarf. A white dwarf, again, is the size of our Earth, but it's got half the mass of the sun. So think of something the size of our sun, half of that mass, the size of the Earth. The star is so dense, if you took a teaspoon of it, it would weigh about a ton. So we're talking about some really dense stuff here in a white dwarf. And white dwarfs, the nuclear fusion has stopped, and they're just cooling off for 1 trillion years or 2. So that's the size of our a star the size of our sun. So what we saw was the sun here. When it ran out of hydrogen and started forming helium, it started moving off the main sequence into the land of the giants, and then it blew off half of its mass as a planetary nebula and became a white dwarf, and very quickly moved from here down to here. This is the land of the white dwarfs. And that's why sometimes stars the size of our sun are called dwarf stars, because they result in a white dwarf. And we have red and brown dwarfs here as well, M stars. Oh, here's a figure. So the sun is so large right now that 1,300,000 Earths can fit into it. So you take half of that mass and put it in 1/1,000,000th of the space, just to give you an idea of just how dense that is.
Space bags, also used in space, in stars.
What's that?
Space bags.
Okay.
You know, they vacuum pack that stuff down to fit in a really tiny space.
Oh, okay. There you go. Yeah, I don't pack like that. I just cram everything into a suitcase and I'm good to go. So what happens to the bigger stars? This is the movement. 1m means one size, one solar mass, the size of our sun. Here's 15 masses. So we've already gone through this, leaves a main sequence, goes into the red giant branch. So here we have one 15 times the size of our sun. Burns the helium, carbon, but it goes on oxygen and continues to burn. These stars will keep burning until they get to iron. Iron is the last stop for any star in fusion because iron requires energy. It doesn't give off any energy, it requires energy. So as soon as iron shows up in the core, the star is a goner. When iron builds up in the core of a high mass star, there are catastrophic consequences. The process of fusing iron requires the star's core to use energy, which causes the core to cool. This causes the outside pressure to go down, which spreads up, which speeds up the gravitational collapse of the core. So once the star hits iron, it only has minutes to live. It's hard to believe such a massive star burning so hot. All of a sudden, it gets iron in the core, and it's got minutes to live, because a chain reaction happens. What happens is the core collapses, and the iron fusion rate increases because every time it collapses, it gets hotter. But then the pressure decreases, the core collapses faster, and finally it collapses and it bounces off the iron, and you have a supernova. It just explodes, and it can outshine billions of stars in that moment. It's just amazing. Neutrinos get created, and a massive amount of energy gets released. And of course, all of those elements that it's been creating, all the heavy elements, get released into the universe. Right? That's how it seeds the elements into the universe. It's an amazing mechanism. So for a brief amount of time, the amount of light that's generated by a supernova is greater than the luminosity of a billion suns, greater than the luminosity of an entire galaxy. And it's hard to tell from a picture just how bright it burns, but this is a supernova right here. That's gone off. That's supernova 1987. No one has seen a supernova go off near us in modern times, but back in the 1600s, Tycho Brahe and Johann Kepler observed naked eye supernova during their lifetimes. But if a supernova was close enough to us, we would be able to see it during the day. In 1987, the supernova went off about 50,000 parsecs from us, about 163,000 light years. And it's been the most heavily studied supernova in modern history. This picture was taken about 2 weeks after the explosion. This is a Hubble telescope of the remnant of that supernova. You could see glowing rings of gas, and if you look carefully, you can see a shock wave in the center there from the explosion racing toward the rings of matter that are encircling the blast site. And scientists have been studying the changing nature of the remnant rings. They detected the first evidence of a collision back in 1996, so that's about 10 years later. Dozens more hot spots as the blast wave slammed into the ring. So shock waves keep hitting the ring, and they see it lighting up the ring as they interact. The ring is about a light year across, and it already existed when the star blew out, because it shed some of its outer shell about 20,000 years before it went supernova. Because the gravity was getting lighter, it blew off some of the shell, and the debris is going to continue to glow for many decades. There's an artist's rendition of a massive star collapse, a supernova. These explosions leave behind super dense cores known as neutron stars. So once we have a supernova, what's left behind is a neutron star, which is even denser than a white dwarf. A neutron star can have a mass greater than our sun, but only be 12 miles or so across. So you take the density of our sun, the weight of our sun, and put it on Manhattan Island, and then in some cases spin it around 20, 30 times a second, and that's what a neutron star looks like. I mean, you can't even imagine the power behind that explosion. So it's about 1 trillion times more dense than our sun when you have a neutron star. This is my favorite remnant, supernova remnant, with a neutron star right in the center there. It's called the Crab Nebula. It's a nebula that we usually see in the wintertime, but you can see it from the northern hemisphere. This is a mosaic image from the Hubble telescope. It's about 6 light years across, and as I said, the neutron star itself is only about 12 miles across. What's really cool about it is that it went supernova, the star went supernova about 1,000 years ago in 1054 AD. And Chinese and Japanese astronomers back then recorded this event, and they recorded that they could see it as a daylight event, a daylight star, for a number of days. And you know, when I look at this in my telescope, of course, I just see what looks like a cloud. But to think that there are people on this planet who actually saw this thing go supernova and saw that effect during the daytime is just mind-boggling. And to see that 1,000 years later, it's got all these complex filaments. It's a beautiful remnant. So it definitely is one of the cooler nebula in my book because of such history. And there is a pulsar in there. So what happens is this thing is spinning around about 15 times a second. Can you imagine an island of Manhattan spinning 15 times a second? And it's shooting out gamma rays on both ends. And so when we're looking at it, we're seeing it pulse 30 times a second because it's polarized. It's shooting out both sides. It's spinning around, and scientists can measure the pulses of this neutron star at 30 times a second. I mean, from 1,000 years ago, this thing is still spinning around. You can't imagine this kind of stuff. At least I can't. So this, again, was another picture from Hubble about 20 years ago, back around 2000. Had a really productive couple of years back then. So between stars of 8 and 80 solar masses, so stars that are 8 to 80 times the size of our sun, this is what happens to them. They go supernova, and they leave behind a very, very dense neutron star. For longest stars, over 80, we think they collapse into a black hole. That's what all the science is indicating right now. And but that's why we keep putting better and better telescopes, so we get better and better observations, better and better data, and we can really finally hone our theories about what's going on out there. But the strides that we've made in the 25, I guess maybe it's 30 years by now, 30 years of the Hubble telescope have just been amazing. And I'm really looking forward to seeing what the first pictures from the James Webb scope are amazing. The clarity of them, I've seen some really cool stuff. And I'll show you some stuff that Hubble showed us a little later when we talk about black holes that'll just blow your mind. So this is a diagram we've talked about. The stellar nebula collapsing into a protostar. For our average sun, we've got the sun here. At the end of its life, turns into a red giant, blows off a planetary nebula, white dwarf remains. 10 to 20,000 years, the nebula is gone, and the white dwarf is around cooling off for a couple trillion years. For a massive star greater than 8 solar masses, it can go one of two ways. It will turn into a red supergiant and then go supernova once we get some iron in the core of that star. And we've seen how it turns into a neutron star for solar masses between 8 and 80. Over 80, we get a black hole. And that's we're gonna take a look at that now. Oh, this is another. If you like to really get complicated over things, you can look at stuff like that. And the old supernova classification system is just, we've discovered so much through the Hubble that it's not a very good classification system anymore. We used to have like 3 or 4 different categories of supernova. Now we've got about 16, 18 categories of supernova. There's many different flavors that we're coming to realize. And I don't know if they're going to give up on the old classification system. There's always a whole lot of rewriting to do when you would do something like that. It's kind of like the magnitudes of the stars. It's an outdated system, but we're still using it in 2022, even though it's a couple thousand years old, and really we have to use a little duct tape to make it work for us. Just another, you can Google the life of a star, and you can get all kinds of really cool diagrams to look at. So this is an artist rendition of a black hole. You know, as I said, about 80 masses. Once you go over 80 masses, what's left behind is a black hole. And you can't see a black hole because the gravity is so intense that light cannot leave it. Although Hawking's has proved that there is some evaporation, but we just can't see it. If you compress the sun to a black hole, it would be about 6 kilometers in diameter. So that's really compressed. We have seen the best evidence of a black hole yet, and that's it. What you're not really looking at a black hole, but what you're looking at is what's known as the event horizon. So a black hole is super dense, and it's just sucking up any matter that's close to it. And as the matter goes into the black hole, it spins around and it heats up, and that's what we're seeing here. And we had some great pictures. There was a team of astronomers. It took them about, I think it was about 3 years to write the algorithm to really process this data properly to get this. And this was just before COVID. I guess it was around 2018, 2019. This was on the front page of some newspapers. And so we could see the event horizon. This came out of the Virgo cluster. It's the heart of M87. So this was located here. That's M87 in the Virgo cluster. That's the black hole's home. About 55 million light years from Earth in the constellation Virgo. And unlike the Milky Way, which has really cool spiral arms and stuff, this is called an elliptical galaxy. It doesn't really have much of a shape to it, just a bunch of stars. But that's where we found the image. So one thing that Einstein's theories predicted was something called gravitational lensing. He said that really, really supermassive objects like a black hole should actually bend the fabric of space-time, and that if there was a very massive object, we should be able to use it as a lens and see stuff behind the supermassive galaxies that we couldn't see visually because they're blocked by it. So in other words, that the mass of these galaxies would actually bend space-time enough so that the light would go around them, and we could see that. And finally, we've seen it. There's gravitational lensing. It doesn't look all that impressive, but it really is quite a step forward. This is a galaxy that actually lays behind here, but because of the gravitational lensing, it's a very distorted image, but these streaks are part of the galaxy that we see, and that proved Einstein's theory to be right. It's estimated that galaxy is about 10 billion light years away. And again, whenever something's 10 billion light years away, it means you're looking back in history 10 billion years ago. at what we're looking at. The the universe itself is estimated to be about 13.8 billion light years old. So this is getting pretty close. We've come within about 400 million years of the beginning of the galaxy, universe, we think. And that's a lot of that is measuring the redshift of objects. Let me see how much time I have. Okay. So here's a really cool gravitational lens, my favorite. It's called the Einstein Cross. And again, we have a very dense group of galaxies here. And this is an enlargement of this square box. And you can see 1, 2, 3, 4 stars there. What you're looking at is one star that went supernova. And the massive galaxy, and it's got a really crazy name, MACS, and a lot of whole numbers after it, cluster of galaxies. But the supernova, the light from the supernova was bent in space and appears in 4 different places. It's the same supernova, slightly different timing in the explosion, but they call it the Einstein Cross because it makes a cross. But to me, that's just amazing. Multiple images of a supernova created by bending the very fabric of space-time. And that just used to be only science fiction, but here we are showing that it's real. And the scientists, don't ask me how they do this, but they're predicting there's going to be a 5th image in less than a decade. I have no idea how they predicted it. Don't ask. And so we've gone through all of the possible outcomes of massive stars, from our sun to 8 to 80 solar masses, and then 80 plus. We've seen white dwarf as a result, supermassive stars, and black holes as well, neutron stars and black holes as the 3 end results. So thank you very much for attending, and
All right.
we got questions. Got a couple minutes for questions.
Yep. All right. So I want to thank you, Walt, for giving us another presentation. I want to thank everyone both here and on our online chats for also joining us. So we are going to be doing a question and answer session. For those of you here, I ask that if you have a question when I call for them, we keep our hands raised, just because I have to pay attention to where I'm walking so I don't accidentally step on someone. And sometimes I get halfway there and then go, oh God, you disappeared. Because there's a lot more of you than there is of me. How I just ask that you wait till you get the microphone to ask your question. Because chances are, if you have a question, someone else also has a similar question and might not be so brave as to ask it. Because I did notice a couple of you got here in the middle of our presentation and did miss the safety briefing, I'm going to go over that again. So we do have the porta potty to my right, your left. Hey, Chris, can you turn on the light to that thing? Right. We also have a little gift shop and museum area in the door to the house. To my left, your right. It looks like we do have several observatories open. We just ask that if you are feeling under the weather and you have the option to look through an eyepiece, perhaps refrain, because we do like to keep people safe and healthy. Right, so with that, we're going to get going into our question and answer session. And the first question is an online question. And you had mentioned at the beginning of your presentation magnitude as viewed by the Hubble telescope on that little chart where it could view up to 30. Do we know what the James Webb telescope, what range that has?
Just over 34.
Cool.
Yeah. So it gives us a few more degrees of magnitude.
Right. Does our audience here have a question? Perfect.
And the other thing about the James Webb is it's got the latest instruments, where the instruments on the Hubble were 25 years old. So we've got some state-of-the-art instrumentation, which makes just as much a difference as the extra light sensitivity.
Okay, hi. My question is, how many black holes are actually in the vicinity of the Hubble, and how many can you identify?
That's a great question. Um, the Hubble is orbiting the Earth, and so the closest black hole is at the center of our galaxy. And you, if you look at the constellation Sagittarius, you would be looking towards the black hole that is at the center. Scientists believe that most galaxies will have a black hole at the center. And again, we can't see black holes directly. We can only see an event horizon, or we can see the effects of a black hole, right? You could see, sometimes you see a big perturbation in an orbit, right? The orbit's not going the way you think it should go, and that's because there's some massive object that you can't see that's affecting that orbit. And as I said, we have the event horizon. Sometimes you see the matter heating up around it, so we can see the effects of the black hole. And yeah, we think that there's billions of them out there. Yeah.
Right. So our next online question is, we always see comparisons of the sun to larger stars such as Betelgeuse and Arcturus. What do some of the smaller stars look like compared to the sun, or even like the moon? Like the smaller stars than
Yeah.
our sun.
Yeah, there's brown dwarfs and red dwarfs, and they are so dim that they're very, very hard to see. And of course, because they're so small, they also have a much less gravitational effect on those stars around them. So they're hard to detect and hard to see. They're very small. But the white dwarf is the size of the Earth, and so some of the brown dwarfs would just be a little bigger than Jupiter, have a little greater gravity than the planet Jupiter. Yeah.
Right. Do we have another question from?
Yeah, up
Ooh,
front we have
there's
one.
a lot of them.
Do black holes ever like die out?
That's a good question. Stephen Hawking talks about evaporation, uh, but it's going to take so long. I have no idea what to. When you look at a white dwarf, it takes a white dwarf trillions of years to cool off. We think, right? Because the universe is only 13.8 billion. To say something has a lifespan of 1 trillion years, it's an educated guess, but that's exactly what it is. So a black hole, it's going to take so long to evaporate that you might as well say it's permanent. Maybe it'll evaporate in trillions and trillions and trillions of years, but I haven't read any really good information on that. Good question though.
Right. Next online question was, do we know how small stars get before the point where they ultimately complete the collapse?
Real small. Well, what happens, take our sun, which is one of the smaller stars. It's going to blow off half of its mass. So it's going to shrink by half. So when you get the white dwarf, which is a very small star, it's going to be about half the mass of the sun. But that mass is going to be so compacted that it's going to be the size of the Earth. So when you look at white dwarfs out there that are cooling off, they're the size of the Earth, a little bigger, a little smaller.
All right. We had another question here.
I can speak up. It's fine.
The online
Oh, I
audience
see.
can't hear
I
you
see.
then.
Sorry. Anyway, so for the iron chain reaction you were talking about in the core of a star, will that occur the moment the first molecule appears, and then it'll just begin from there in a matter of minutes? You said, or
Yeah, once I can't tell you what quantity of iron there is, but it accumulates very quickly when it gets to that point, and it sets off. What it does is it sets off a couple of pulses, and then it goes supernova. Yeah.
Right.
I think we have one. Oh, you got an nylon?
Yeah,
And we've got one up
I'm
here,
going
too.
back and forth because I have a lot of questions here and a lot of questions
Wow.
there. So I'm trying to give everyone a fair chance.
That's great.
Right. Is it possible to feed a sun or star to increase its lifespan?
Hmm. You mean like protein?
I
Well,
mean, if it's going to the gym to get those sick gains,
there
but
are actually, I joke around, but there are actually, we're very separate from the stars around us. The nearest star, Alpha Proxima, is about 4 light years away. But there's areas of the universe where in a 4 light year cube, you could have hundreds of thousands of stars. And we do know that some stars interact with others. Sometimes binary pairs are very common. But for one star to grow, the other star's got to shrink because the gravity of the winner star is pulling mass off the other. So if you want to prolong a life, you got to destroy another star. You got to find mass to feed it to make it bigger.
right. I know there was a question right here.
Yeah, if you go like, you know how the black hole is like a tunnel. If you like go somewhere else, will you like see a tunnel because it's like
Like
endless?
wormholes and that kind of stuff.
Yeah.
That's a lot of that's a lot of fun to think about. But to travel in a black hole, as far as we know, is impossible. I mean, forget the fact of you know taking centuries and centuries to get there, but the gravitational tides on just me, if I were to jump into a black hole, the difference in gravity between my feet and my head would be so much that it would stretch me out thousands of miles at least into a Mr. Spaghetti Man.
Meat spaghetti.
What's that? Yeah, it's actually the tidal forces. The difference, the black hole is so massive that the difference in the gravity between one spot and 6 feet away is enough to just stretch out.
Right.
But obviously we don't know exactly what happens in that black hole because we just can't see. We can see the matter going in, but we have no idea what's going on in there. We can only do mathematical equations that I have no idea what they mean.
Right. So, you had mentioned that NASA and the JPL labs does color their photos. Um, and someone asked, aren't there multiple types of colorways to colorize astrophotos? Like you have uh different standards, like, oh, this one might use, I believe they're referring to where like this one might use blue for oxygen and the other one uses yellow for it, or I'm not quite sure of the colorways. I am not an astrophotographer.
Yeah. So for scientific research, they try to color the elements the same. Hydrogen you always see as red, hydrogen alpha as red. And that is actually, if you use color film as an amateur astrophotographer, usually if you're going to use like a camera that wasn't made especially for astronomy, you try to take the red filter out so it doesn't filter the red out. And you will get red on there. When it comes to stuff that you see in magazines, it could have scientific coding, or it could just be coding for the prettiest picture you can get. I mean, a lot of people who take astro photos will go to Photoshop and they'll punch up colors, they'll punch up contrast, and they'll be looking to make the most spectacular kind of photo for a visual to look at, and it doesn't have scientific data value. It has aesthetic pleasing value when you look at it. So a lot of the stuff you see are really aesthetic, but scientists do color code it for what elements they're seeing, and they also use spectrometers to look at to look at what colors are being absorbed by the star, because that's how they tell what elements are in the star. And they also look at it for redshift, so they know what the spectral signature is of a star. And as the faster a star is moving away from us, the more that spectral signature is shifted to the red. So the spaces stay the same. So the signature of the element, say oxygen, stays the same, but the whole signature is shifted to the red. And the more it's shifted to the red, the faster it's moving away from us. And that's how they judge not only distance, but that's how they're measuring the rate of the expansion of the universe.
Right. Was there more questions from our audience here? Oh, There we go. Sorry, I'm a little blind in the night without my glasses, and I don't know where they are because it's dark.
So one of the things you didn't mention was star clusters. I'm particularly interested in it. Can you give information of how those form or what they actually are?
That's yeah, like the globular clusters. I'm not really up on that. There's about 102 globular clusters around this nucleus, and they're gravitationally attracted. I mean, there's some star clusters you see that happen to be in the same part of the sky, but there's open clusters and there's globular clusters, and there is a gravitational attraction to them. But I couldn't tell you exactly how they're formed. They're formed as part of the formation of the galaxy. But that's about as far as I can go on that. Great question. That's Google material. And that's what I hope. When I do talks like this, I really hope that there's a half a dozen or a dozen people who go home and do some work. I can just give you a taste of the science, but if you spend a couple hours looking into sites on NASA, JPL, and some of the other sites, you can learn an awful lot. And you know what? The stuff here is much more amazing than Star Wars. Star Wars is all fake. The stuff we're looking at is real. The power and the beauty of the universe that's really out there is stunning, and it's better than anything we can think up ourselves. So I would spend more time watching science documentaries than Star Wars fiction.
All right, and that is actually a good point to make.
I do like Star Wars, by the way, Mr. T-shirt.
Yeah.
I went to the Star Wars fanvention in New York this last couple months ago, so I won't say I don't watch it. I'm just saying, check out the documentaries on the real star stuff.
Right. Yep. Like I was saying, amateur astronomers also do contribute heavily to the science that people do. There are amateur astronomers who are associated with this club or were actually helping find exoplanets. So if you have a topic of interest in space and whatnot, chances are, even though you might not be formally part of a lab, you can probably help make that science more concrete or find out more. So
that's a great. Let me just piggyback on that, because that's a great point. If you Google citizen science, you could put exoplanets, or there's something called the Galaxy Zoo, where you can sit and you can classify galaxies because they have so many pictures, they don't have enough time to classify them all. You can really do some important work to help science gather, classify the data that scientists already have.
All right. So our next online question was, what will our galaxy look like in billions of years? Will it be full of black holes and neutron stars?
Ooh, it will have some. What's really cool, the general expansion of the universe is that everything's moving away from everything, but locally there are things that move towards each other. And there's the Andromeda galaxy is about 220,000 light years wide, and it's the closest galaxy to us. And you can see that in the summertime. So that's about 4 times the size of our galaxy, the Milky Way galaxy. And the Andromeda galaxy is moving towards us. It's about 2.5 million light years from Earth. And I think I wrote that. Yeah, the Milky Way and Andromeda galaxy are going to collide in about 4 to 5 billion years. Of course, that's not a concern to us because our sun's going to be starting to be end of life. But the Andromeda galaxy and the Milky Way galaxy will collide in about 4 to 5 billion years. And there's a lot of space between stars, but you can see, if you go on Google, you can see galaxies that interact with each other and join, and they form new stars. So that's what we're going to be looking like in about 4 to 5 billion years. We're going to look like 2 galaxies coming together, forming some new stars, and just looking really funky.
All right. Was there another question out here? Oh, we got another one.
So I apologize if you did mention it. I just don't entirely remember. But in terms of like superclusters, I know I believe we're inside of the Laniakea supercluster. But with the James Webb Telescope, do you think we'd be able to see or at least learn more about that and maybe what's beyond it in terms of like the great attractor and stuff like that? Or because I know that's a lot of just mysterious stuff right now.
Yeah, the James Webb the James Webb Telescope will help us see more of that. Um, it's going to help us understand the evolution of galaxies as well, um, and it's also going to help us understand some more astrophysics. You know, when the Hubble first went up there, what they did was they pointed it at a spot in the Big Dipper that looked like it had no stars, that it was empty, and they came up with about 1,500 galaxies, and everybody oohed and wowed, and so they started out by pointing it towards blank spaces. Then they started pointing it towards the supermassive spaces, and they started seeing stuff like gravitational lensing that I showed you. And so, no matter where you point that telescope, you're going to learn something. It depends on who's got the grant money and what they're studying at the time. But there are just so many different areas to study. There's a lot of black hole research to be done. You name it.
Right. So I do have an online question that jumps off of a question that was asked in person earlier, and I'm going to paraphrase a couple because I've seen a couple different versions. But uh, when a white dwarf cools off, would it turn into just like a space object, like a meteor or a planet? But so is it just that we haven't seen anything past the final forms, like the black holes and neutron stars, or is there nothing past those final forms?
Question. We have not seen a white dwarf go through its end of life cycle because it takes so long. But you know, we've got dark energy, dark matter. You know, what we see out there, the matter that we can see does not account for all the stuff that we're seeing gravitationally. So there's a lot of dark matter. We just have no idea what it is. Right now we're postulating what it is, but I'm not sure how they're going to figure that one out.
All right. Was there another question in person? All right. So we're going to move on to our next online question, which is actually a couple. When you jump into a black hole, why stretch and not rip? Do we suddenly have elasticity, or do you mean more in the cartoon meat grinder effect?
I don't want to find out.
I'm with you there. I really don't personally want to find that one out.
I tell you, I'm not all that flexible, so I'm guessing that I would just be pulled apart by gravitational waves, by tidal forces is what I was really talking about. I don't think I'd be able to stretch to spaghetti.
Right. Question here? All right. So the next online question is actually a restatement because I missed it earlier. I saw it, but apparently somehow I ended up skipping it. How do we know the density of stars just from and like their composition? Is it just from the sheer amount of math people can do?
Math has a lot to do with it, and having dropped out of engineering because of the math, I can't say I understand it. But you know, observational data plays a lot. You know, when you look at what the size of the object is, and then look at what the gravitational force is, how it affects objects around it, you can start to see how massive an object is. But there are many different ways of determining it. But you know, gravity is a big part of it. You know, how does it affect the objects around? What's the size of it, and how does it affect objects around it? And that gives you an idea of how massive the object is.
All right. Someone had actually looked up an online chat, uh, apparently in their spare time, black hole physics, and their response to it, you could think of it as being ripped too, but not like Laffy Taffy breaking at one point, but literally all of the atoms that make up the falling object uniformly separating and falling downwards.
Okay.
Which sounds very dramatic and yet very calm and peaceful at the same time.
I was thinking painful, but okay, calm and peaceful.
Well, I mean, it's not, you know, going screaming off a roller coaster at how many miles an hour. All right. Was there any last questions for our in-person audience here? All right. I'm just gonna
You've
see.
asked some great questions, and I really appreciate the thoughtfulness behind them.
Yeah, and there's a lot of chatter in chat, so it's actually sometimes a little hard to pick out the online questions from the chat. So
Now, the questions are very encouraging.
let's see. Right. So it looks like our online questions are also done. I'm sorry, you guys, if I missed any. You can always leave them in a comment on our YouTube videos. I may not immediately get the answer to them, but I will eventually get around to answering all of them if I don't get there. I want to thank you all again for coming out, and I want to thank our online audience for joining us there. If you like these programs, we are a nonprofit, so we do kind of exist off of your guys' generosity and keeping us going from the donations, either through things you buy at the sales desk or even through things like the Patreon we now have. Also, you can support us non-monetarily just by liking and subscribing to our Facebook pages and YouTube. Again, for any more information, you can also check out our website. It has all of the links for our socials as well as what we do here, and that is uacnj.org. And I want to wish you all a good night. And you guys, like I said, we do have a couple of observatories open. It kind of looks like we're a little overcast. I could see a couple of stars, so I don't know what they can get, but hopefully they'll get you some interesting views. Have a good night.
Thank you.